So there are a few benefits to actually having this simulation in VR. The biggest of which is kind of a sense of scale. You get to see, what it might actually look like in real life, and then once there's deflection applied to the beam, you can see, how that might simulate in real life. Whether it might snap, so on and so forth. Actually, increase this so it's bigger. But so there you go. You can see how you actually get better. And that's actually how it would be functioning in real life. Let me make this more realistic. So I'm gonna make its height thinner sense, but we'll make it like a 2x4. So this would be like, probably 4 depth. Well, actually, it means its height needs to be 2. We can make its length a little shorter. Okay. So now when I start adding force, it should be much more obvious. Yeah, there, you can see it bending immediately. The whole idea with this is that this would eventually turn into like a whole suite of different physics simulations. We actually presented this at USF for their civil engineering conference. But it's cool having it in virtual reality because you're not just like seeing a simulation of it in two dimensions. You can actually interact with it, grab stuff, pull it, and all that. That's the cool part of it. So for example,
so how would you use this?
Okay, right, yeah, that's a good question. Instead of just having one plank, we actually haven't fully fleshed it out yet. But the end game would be kind of for example, they put four planks together, put a roof over it.
It's like a house.
Exactly, and start adding weight.
So you could
roof.
build a house in here and then see how it works. So then
you can observe all of the different forces going on, see where it might break, or where you need to reinforce stuff. And just by changing, for example, this variable here, which is the elasticity modulus, I'll change this from wood to
so
steel.
Did you code all of that?
Yeah, so here, I'll show you here. This is, it's not too much, it's 300 lines, but the code came from this portion right here, which is pretty much just taking, so obviously it's doing, first it calculates the max of deflection downwards, and from there it can derive a quadratic curve from here up to the points, right? So it's actually deflecting down, and then once it gets that, it loops through each point and creates triangles across. Once it has all those triangles, it puts a mesh over them, and that's how you get to actually see it.
Oh.
Yeah. So this is all the math behind the actual simulation. We started out with just calculating a max deflection point, and that is derived with just this equation here. This is a given with our ID equation sheet. It's just the force times the length cubed over 48 times the elasticity modulus times the moment of inertia, which is also known as the cross-sectional area. Once that is calculated, it'll give us a straight value that's just how far down it will deflect, given its tensile strength and the amount of force applied. Then from there, we went through and we derived a quadratic equation we can use to go from this middle point outwards and calculate where height-wise these different points will be up the spectrum until it hits the actual pins. And then from there, we can actually move on to the code, and I'll show you how it's represented in code. So you can see that arc there forming on the actual beam, but in code, that same formula that I just showed on the board is right here. Max deflection equals force times math power length 3 divided by 48 EI. And those are all calculated given more standard equations, but later is where the quadratic comes in. Down here, we start to calculate the actual vertices for the different points. Once the vertices are calculated, we can actually layer them together in duplicates and triangles, and those triangles then end to form this mesh that you actually see on the screen.